So last time we finished talking about Boyle's, Charles, and Avogadro's law, so we're just going to do a quick review of those. So what is Boyle's law? Take a second, think about it. And pressure and volume are inversely related. Inversely is very important, meaning when volume decreases, our pressure will increase. So for inversely means when one increases, the other decreases. What is Charles' law? Charles' law is volume and temperature. Volume and temperature are directly proportional. So if we increase the temperature, we're going to increase the volume. And lastly, Avogadro's law. The number of moles and volume are directly proportional. So now instead of having to remember all three of these laws, what we're going to do is write what's called the ideal gas law, which is going to combine all these, and we can use these in our calculations. So PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, T is the temperature in Kelvin. Remember, Kelvin's important. Try to remember why do we use Kelvin and not Celsius. And then R, the ideal gas constant. You can see the ideal gas constant is 0.0821 liter atm per mole Kelvin. And the ideal gas constant is what it says, it's constant, so it does not change. You are always going to use that value. And one thing you can, instead of having to remember each one of these Boyle's, Charles, and Avogadro's law, I'm going to write something called the combined gas law, where we know that R here is a constant. R is the constant, so we're going to be able to drop this and write the called the combined gas law. So PV divided by NT is equal to PV divided by NT. We have P1, V1, N1, T1, P2, V2, N2, T2. And now if we have a constant number of moles, say for Charles' law we have pressure, volume, where we have a constant number of moles and constant temperature, these two denominators are going to be the exact same. So it's not going to make a difference, and when you drop those two, it'll become just like Boyle's law. Now, the same thing is going to occur if we could see Charles' law out of this. If we have constant pressures, these pressures are going to drop, and the constant number of moles is going to drop, and we're going to be left with Charles' law. And then you should be able to see the same thing for Avogadro's law. Now, so if instead of trying to remember each individual law, you can just remember right here the combined gas law, and that's going to include all of them in one. So here's a sample problem. You can give it a try, and using the ideal gas law. And the answer you should have gotten is 3.27 moles. So let's see how we do this. We took the ideal gas law, which was PV equals nRT, and the question asked determine the number of moles. So we solved for N in the equation, and we substituted our known values in for pressure, volume, the gas constant, and temperature. And if you notice, now our units are going to cancel when you're left with moles. So liters and liters, pressure, pressure, Kelvin, and Kelvin. Remember, and we converted to Kelvin there. It was in Celsius, but we converted to Kelvin. And now we are left with moles, which that is 1 over mole, which is equal to mole. And that is how we solve that problem. Now, in the real world, it is rare for us to have a single gas in a container. And I want you guys to think about what's the air? what gases make up air? So what makes up air, we have nitrogen, oxygen, CO2, hydrogen, some helium. It's a mixture. And the mixture then can give us a total pressure. And we can find that total pressure by the sum of the individual pressures. So the pressure of the nitrogen plus the pressure of the carbon dioxide plus the pressure of the oxygen in your car tires gives the overall pressure that you read from the gauge. I want you to notice this last line here, very important. Pressure is affected by number of particles, not type. So the pressure is affected by number of particles, not type. So we look at this picture here, the first one, we have 1.75 moles of helium and has a pressure of 8.4 atm. And the next one, we have 3/4 of a mole of hydrogen, 3/4 mole of helium, and 1/4 mole neon to have a total of 1.75 moles of gas, and we have the same pressure. And finally the last one, 3 different gases again with different amounts. 1 mole nitrogen, half mole of oxygen, 1/4 mole argon, but once again the overall total number of moles is 1.75 and the pressure is 8.4. So the number of particles affects the pressure, but not the type. And if the total number, so the total number of moles is the same, we're always going to have the same pressure. So go ahead and give this problem a shot. You need to calculate the new pressure when that valve right here between the two vessels is open. Should have gotten 2.25 atm. Now how we do this is we're going to calculate the new pressure on the left side when the valve is open, and then we're going to calculate the new pressure on the right side when the valve is open, and then we add them to get the total pressure. So we have 2 atm, and we're going to use Boyle's law here. So we have 2 atm times, we have 9 liters is equal to our new pressure times, now our new volume when we open up that valve is going to be the sum. So 9 plus 3, which is 12 liters. And when we do algebra to solve that out, we're going to get a new pressure of, so P2 is equal to 1.5 atm. Now we're going to do the same thing on the right side. So 3 atm at 3 liters is equal to P2 at 12 liters. And doing algebra, our P2 should be 0.75 atm. And we add 1.5 and 0.75, we get 2.25 atm, our new pressure after we open up that valve. Here's another sample problem that you guys can do with the answer shown there, making sure that you can calculate the pressures and then add the pressures to get the total pressure. Now, in science, we know what happens, but we also want to be able to explain it. We want to explain why does the volume change when we change pressure, or why does the temperature change when we're changing the pressure and volume, when you noticed in doing that simulation. So the kinetic molecular theory, we have a series of 5 assumptions which is going to show us why that happens. The very first thing, assumption 1, is that gases consist of large numbers of tiny particles that are far apart relative to their size. So we take a look in the first picture. We have a solid. All these particles are in a packed uniformly. You can see a nice sort of crystal structure. And then next we have the liquid, where the particles are still very close together, but they are not. They can slide around. They can slide around and acts like a liquid. So the liquid is going to take the shape of its container. And on the right we have the gas. We have a large number of particles, and they're the tiny particles are very far apart. We can then make an assumption, soon you'll see in a bit, that they don't interact with each other. Assumption 2. The collisions between the gas particles and between particles in the container walls are elastic. So this means that you want to think of them as like pool balls. The elastic collisions, each gas molecule, when it strikes another gas molecule, is going to bounce off. It's going to bounce off and then keep going. It's going to maintain its kinetic energy. So just like playing pool, you can make a bank shot off of the bumper on the side, and it's going to come off with the same speed that you shot it in. Assumption 3. The gas particles are in constant, rapid, random motion. So these gas particles are constantly moving around inside of that container, such as you see there, and they're bouncing off that wall. They're going to bounce off and it's going to maintain that kinetic energy. Now, assumption 4, there are no forces of attraction or repulsion between the gas particles. This is again where the pool ball analogy comes in. The cue ball is going to strike those other pool balls and they're going to bounce off. The energy that came in with the pool ball is going to be transferred, the kinetic energy, to all the other balls, and they're not going to stick together and form new compounds. So if we want to think about two hydrogen atoms, or two helium, let's think two helium atoms bouncing around in a container, they're going to bounce off each other. They are not going to stick together and form a new compound. They're going to bounce off with the same force that they initially struck each other. Now, assumption number 5, the final one. The average kinetic energy of gas particles depends on temperature. Now, you may have noticed this in your simulation for the lab report, but as you increase the temperature, the gas particles start to move faster. The gas particles start to move faster inside of the container. Now, if we decrease the temperature, they start to slow down. And some of you are able to get the gas particles all the way to absolute zero, which they either vibrated just a very small amount, or if you had the light species, they froze completely. And all gases at the same temperature will have the same average kinetic energy. So once again, the average kinetic energy depends on the temperature, and all gases at the same temperature will have the same average kinetic energy. So if you look inside this box right here, we have some big gas particles and some small gas particles mixed around. Those two are going to have the same kinetic energy. One might be moving faster than another, but this is the equation for kinetic energy, which you do not need to know. But the mass, a larger mass particle is going to move slower than a lighter one, which will move faster to have the same kinetic energy. Here's another problem. I told you would have to be able to sketch graphs of this. So I want you to sketch a graph of pressure versus volume at a constant temperature and number of moles. Here's that graph. And now you should remember that for pressure and volume, you cannot have a zero volume. So if you see here, the graph is like an asymptote. As it approaches zero, it starts to increase exponentially. Reason why is if we have something in our box, we cannot compress that box to zero because we have particles inside of that box. Now, you can sketch a graph of volume versus temperature. For volume versus temperature, we can see we have a direct relationship. As volume increases, the temperature increases. Now finally, sketch a graph of volume versus moles at constant temperature and pressure. So here, as we increase the number of moles, we're going to increase the volume of our container. And that is assuming that we're going to remain at a constant temperature and constant pressure. Now finally, all together, we're going to use the ideal gas law and the Dalton's law of partial pressures to solve this problem. So what you should have gotten is a total pressure of 2.88 atm. Now how we do that is the question tells us the vapor pressure of water was 1.73 atm, and then it tells us we had 0.245 moles of argon was collected in a 5.20 liter container at 298 Kelvin. So we want to know the total pressure, so that also includes the pressure of argon and water. But first we need to find the pressure of argon. So we're going to use the ideal gas law, PV equals nRT. We're going to solve for pressure. So you just divide it by volume here. So from here to here, divided by volume to solve for pressure. And then we're going to substitute what we know into the equation. Once again, using our ideal gas constant, and we see that our units are going to cancel. Very important you show units here to get our pressure. And now we have the pressure of argon. Then using partial pressures, because the total pressure is the sum of each gas's individual pressure, we're going to sum the pressure of water and pressure of argon to get a total pressure of 2.88 atm.